we have a flow field which is given by u equal to x and v equal to minus y. And in this particular problem, we are asked what is the flow rate through a given surface AC. So let me draw a coordinate system. Okay, so let me draw an arbitrary line AC. Let this point be 2, 5. Let this point be 3, 2. So that this delta x is equal to 1. This delta y is equal to 3. So given this particular prescription of a flow field, the question is what is the flux through AC? And let us assume a unit width into the plane. So first things first, we can do the following. We can draw this, we can find out the equation of this line, we can find out the corresponding equation of the normal. Say the normal is n, and because it's a straight line, the direction of the normal is not going to change. And if that is the case, the flux that we want is going to be integral u dot n dA going from A to C. And actually this dA is going to be ds. So this is going to be integral u dot n ds, because the area is going to be this length multiplied by the width into the paper, which is equal to 1 in this particular case. So now we know that the velocity at any point is given by this. So once you know the equation of this line, you know the components of velocity at all points on the line, and you can do this laborious integration and find out the total volume. But we're not going to do it like that. We're going to make use of certain properties of the flow field. Notice that del u del x plus del v del y is equal to 1 minus 1, and it is equal to 0. And this implies that the flow field is incompressible. And we know from the elementary considerations of a stream function, an incompressible flow field can be written in terms of a single scalar which defines the stream function. So we can write u as del psi del y and v as minus del psi del x. And you can of course swap the sign of this. It makes no difference as long as you keep the signs consistent. So if this is the case, let us make a small segment over here of length ds. So yeah, okay, it's already drawn over here. So let me reuse this diagram. So this is ds. Let us project ds along these two directions. So this is going to be dx and this is going to be dy. And dx and dy are in this directions, note, because y is pointing upward. Now, if a flow is said to be incompressible, it means that whatever volume enters into the control volume will also exit the control volume. or equivalently the net volume entering has to be 0, meaning whatever volume enters must be the same as volume exits. Alright, so this is something which is implied by the condition of a flow being incompressible. So this, not again, this is the property of a flow, it is not the property of a fluid. And so we can write for this particular control volume, right, let me call this small a, small b, small c. So for control volume ABC, I can write the Reynolds transport theorem as ddt of, I mean, I can write this, so it's not just valid for ABC, but it's valid for everything. So integral ddt f dv plus integral u minus b dot n dA equal to 0, where b is the relative velocity, and in this case it's the relative velocity of the control volume. So the relative volume, the relative, rather b is the velocity of the control volume, and u minus b is like the relative velocity of the flow with respect to the control volume. Okay, so in this case the control volume is stationary and hence b will be equal to 0, and let us choose f to be equal to rho. So we have ddt of integral rho dv plus integral u dot n dA equal to 0, and because mass cannot be created or destroyed, this has to be 0. It's a steady flow. So now if integral u dot n dA is 0, then it means that integral, so let me redraw that particular diagram. It means that integral u dot n ds going from A to C plus this contour, integral u dot n ds going from C to B plus integral u dot n ds going from B to A, that has to be equal to 0. And integral, if I rearrange this, integral A to C u dot n ds is equal to integral, so now let's just reverse the limits. So this entire thing will become integral u dot n ds. So now this is going from B to A, but it will go from A to B plus integral u dot n ds in going from B to C. So if an integral goes from A to B, the ds will be equal to minus dy. So this is integral A to B. This will be, so what is u for this particular phase? So the u velocity is this by convention, and the v velocity is this by convention, and the normal over here is this, and the normal over here is this. These are the outward normals. So u dot n cap in this case will be minus u, and ds will be equal to minus dy. Alright, plus integral going from b to c. Now u dot n cap in this case will be minus v, and ds will be dx, and thus this becomes integral a to b u dy minus integral b to c v dx, and u by the definition is del psi del y, and v by definition is del psi del x, minus del psi del x. So this becomes integral a to b del psi del y dy plus integral del psi del x dx going from b to c. Now integral a to b to c is tantamount to one single integral from a to c through b. So this becomes integral del psi by del x dx plus del psi by del y dy going from A to C, and this term is essentially integral A to C d psi, because this by very definition of the chain rule is equal to d psi, and this simply becomes psi C minus psi A. So therefore the flux through this particular surface is simply equal to the difference in the stream function between the 2 points, and this is true regardless of the curves joining A and C. It can be anything. Alright. So now it's just a matter of finding out psi C minus psi A. So for that purpose we must find out what psi C and psi A are. Let us do that. So u is equal to x and v equal to minus y. So now u is del psi del y and this is equal to x, meaning psi equal to xy plus fx. What is del psi by del x? This will be y plus df dx, and this is equal to, so from this particular statement we can write minus del psi del x equal to minus y, implying del psi del x is equal to y. So del psi del x is equal to y and this is going to be this equal to y. So y can cancel out and this implies df dx is constant. So the stream function is psi equal to xy plus constant, and we can choose the constant so that at x equal to 0 and y equal to 0, c equal to 0, and hence the c can be chosen to be 0. So the stream function is simply psi equal to xy. Now coming back to the points under consideration, the first point was 2 5 and the second point was 3 2. So psi, so this is point C, this is point A. Psi at point C is equal to 6 and psi at point A is equal to 10. So the flow rate Q will be equal to 10 minus, rather 6 minus 10 is equal to minus 4. Alright. This is essentially the integral u dot n cap dA going from A to C. Now you can actually verify these integrals, and I'm just gonna do it very quickly. So the integral going from A to C u dot n ds, it came out to be integral of, so what was it? Let us, u dy going from A to B and minus v dx going from B to C. U dy going from A to B minus integral v dx going from B to C. And 2 5 3 2. So this point is 2 comma 5, this point is 3 comma 2. Alright. So integral u dy, so u is equal to x, so this becomes integral x dy going from point A to point B. So this is going to be x times b minus a. So b minus a is going to be, so the y coordinate, so y at b minus y at a, and this particular integral is equal to, so x value is going to be 2 and y value at b is equal to 2 and at a is equal to 5. So 2 twice 2 minus 5. So this integral, let me make it pink. So this is going to be integral b to c v dx, and v is equal to minus y. So this is what it becomes. So this becomes y. So this is going to be twice times dx. So x at c minus x at b. So this becomes twice multiplied by, so x at c is 3 and this is 3 minus 2. So this becomes minus 3. So this becomes minus 6 plus 2 and it comes out to be minus 4. And it is the same answer that we have. It's quite obvious because essentially we are able to represent the flow through only a single scalar, and this entire calculation is a testament to that. Moreover, why is it valid for any kind of curve? You may have the question, I mean, is it valid for this? Is it valid for this? And the answer is yes. You can take any line segment over here, you can project it over ds. So in going from this point to this point on this small line segment, you can make the small projection dy and dx, and you can show that flow rate across these 2 points is psi c minus psi a. So you can discretize this as a whole bunch of points. So let me call this P0, P1, P2, P3. So flow rate between 1 and 0, it would be psi at P1 minus psi at P0. Between 2 and 1, it will be psi at P2 minus psi at P1. So if I add this, the flow rate between 2 and 0, it will be, if you just add these two, psi at P2 minus psi at P0. So you can continue this for any arbitrary line segment and eventually reach the other point, and you will get psi, the difference in the psi or the stream function difference, and that is equal to the flow rate. It's a very simple concept, but it can help you save a lot of time provided the flow is incompressible. As a small homework, you can try to plot the velocity field using MATLAB or whatever you like, and you can try to convince yourself that whatever flow comes in is the same flow that goes out of a chosen control volume. You can also try to draw the line AC and try to justify the entire calculation, that is doing u dot n cap across the line segment AC. It involves finding out the equation of the line, finding out the slope of the line AC, the orthogonal to that direction, and then finding the effective flux. It's quite simple. Have a go at it. Let us move on to the next problem, which involves filling of a tank. Let us consider a tank as shown in the figure. Let us consider two inlets to this tank, rather two ports to this tank. The first port is something like this, and the second port is something like this. Let's not make it divergent, let's just make it uniform. Yeah. So it is given that free stream velocity, meaning a velocity which is constant over the entire cross section. This velocity is given as u infinity. Fluid with this velocity enters into the tank. The tank is full of water and it exits the tank, but during exit it has a velocity profile, something like this. Okay, so this particular velocity profile, so if I draw the local coordinate as x and y, the velocity profile is given as u equal to u naught times 1 minus y square upon x square, where the height is equal to 2h. That is, it goes from minus h to plus h. So now the question is, what is the relationship between u naught and u infinity? It is given that this is also equal to 2h. Okay, so the Reynolds transport theorem can be applied to a control volume as shown. This green line is the control volume. Okay, so for this particular control volume, what are the properties? The velocity at all the faces is equal to 0, meaning none of the boundaries is moving. with this, we can write down the statement of the conservation of mass. So essentially we have ddt of integral rho dv plus integral rho u minus v dot n dA is equal to 0. Now this is going to be 0 because it's a steady state problem, and so whatever mass is contained, it's not going to change. Okay. Whatever is coming in has to go out. It's a steady state problem. So essentially it boils down to integral rho u dot n dA is equal to 0. Now so let me call this 1, let me call this 2. So this is essentially implying integral rho u dot n. So now if rho is constant, it makes no sense to keep repeating rho. We can simply drop it. So integral rho, so integral u dot n cap dA over section 1 plus integral u dot n dA over section 2 is going to be equal to 0. So now at section 1, what is u dot n cap going to be? Now, given this control volume, the normal vector of area at this point will be this. So now u is coming in, so it's u infinity, but the normal vector is this. So it is 180-degree opposite. So u dot n cap will be simply equal to minus u infinity. And therefore, the first integral may be written as integral minus u infinity dA, and this is equal to minus u infinity into 2h, because we are assuming unit width into the plane, or we can assume some width into the plane w, but then w will get cancelled from both sides, so might as well drop it a priori. What about the second cross section? The u is in this general direction along the local x coordinate, and the normal vector to this green area is also pointing along x. So u dot n cap will be whatever this velocity profile is, u. So now it simply becomes integral u dy going from minus h to h, and this becomes integral u naught 1 minus y bar square dy bar h. So essentially this integral I am dividing by h and multiplying by h. So this h appears over here, and I am letting y bar as a new variable as y upon h. So this velocity profile becomes 1 minus y bar square, and this dy upon h becomes dy bar, and the integration will be from minus 1 to 1. This particular integral is u naught h times, so this is going to be y bar, so 1 minus minus 1, this is 2, and this is minus 1/3 y cubed, so 1 minus minus 1, so this is going to be 2, and this comes out to be u naught h, so this is what 4 upon 3. Okay, so this is u naught h times 4 upon 3. So if we equate these, u naught h times 4 upon 3, so this is basically this term, and this particular term is minus u infinity into 2h. This is going to be equal to 0, and this implies u infinity is equal to u naught times 2 upon 3. This is the relationship that we are looking for. Okay. So this problem essentially tells us that given the same inlet height, in order to maintain the same flux, u naught has to be 3 by 2 times u naught. So u naught essentially becomes 3 by 2 u infinity. Okay. So it's just a consequence of the conservation of mass that the velocity over here has to increase. Actually, you might have learned this in your JE times, that A1 V1 equal to A2 V2, and you can easily show that using this, the Reynolds transport theorem that we have learned. So if the average velocity over here is V1, average velocity over here is V2, this is area A1, this is area A2. Note that V1 is the average area. Okay. So now let us choose this control volume, which does not move anywhere. So the control volume has B equal to 0 for all the faces of the control volume, right? In that case, we can write ddt of integral rho dv plus integral rho u dot n dA equal to 0. So now if we could choose a steady state problem, that is the velocities are not changing in time, this particular term vanishes and we are left with integral rho u dot n dA. And if rho is constant, this particular term drops from the integral. So essentially, u dot n dA is equal to 0. And what constitutes this particular integral over the surface, the control surface? So it is going to be u dot n dA evaluated at 1 plus integral u dot n dA evaluated at 2. This is equal to 0. Now at surface 1, u dot n, this thing is minus whatever the velocity is at point 1, at, at this location 1. So this becomes minus u1 dA, integral of that. This term becomes integral u2 dA, because the normal vector and the velocity are aligned, and if the velocity over here, the local velocity is u2, then this is the integral. And by the very definition of the average velocity, this will be average velocity at 2 times the area at 2. And this thing is actually the very definition of average velocity. So even though u2 can vary over this, u2 can vary like something like this, but despite varying like this, you are writing it in terms of what you can measure. So what you can measure is the average velocity. So this is this, and similarly this will be equal to v1 a1. So with a minus sign, of course. So minus v1 a1 plus v2 a2 is equal to 0, and this implies v1 a1 equal to v2 a2. And if you do not want to neglect the effect of density, so rho over here is say rho 1, rho over here is say rho 2. So this rho u, not over here. So say the average density over here is rho 1, average density is rho 2. So this rho u2 dA, it would become rho 2 v2 a2, and integral rho this would become rho 1. As simple as that. Then this becomes modified to this. So this is just a statement of the conservation of mass for a steady state system. And if the density is constant, it becomes a statement of the conservation of volume, and by extension it is the statement of the conservation of mass as well. Alright, let's proceed further to do another tank problem. And in this case, we have a tank like this, which is open at the top, and again we have one inlet, and rather we have two inlets. Okay. So then the question is, what is the rate of change of the height of water in the tank? So the height is as a function of time, and the velocity over here is uniform. It is v1, it is v2. The area is a1, the area is a2. The area of this entire thing is a. So now let us choose the control volume as shown by the green line. So what are the properties of the control volume? For all the surfaces except the pink surface, the velocity of the control volume is 0. For all surfaces except pink. In fact, for the pink surface, we choose, so let me call this surface as say S. We choose S to move with the surface of the water. Meaning dH dt, which is the velocity of the water at the free interface, is also equal to the velocity of the control volume at this particular segment. So now if I write down the statement of the conservation of mass, what do I have? I have ddt of integral rho dv plus integral rho u minus b dot n dA equal to 0. Now what about the first term? It is essentially ddt of, so now imagine that these two limbs are quite small compared to the tank volume. So this essentially becomes rho times A times H. And this first term is essentially rho A times dH upon dt. What about the second term? So now for all the surfaces apart from the surface S, that is the top surface, B is going to be equal to 0. So it is equal to rho u dot n dA not S plus rho u dot n, sorry, for the surface S, it is u minus b dot n dA. Because the surface itself is moving with the velocity of the water. If the velocity of the surface is equal to the velocity of the water, then this particular term, which is the relative velocity of the flow with respect to the velocity of the surface, is equal to 0. That is, u minus b cuts no flux across S. This relative velocity cuts no flux across the surface, because as the surface moves, the area is moving and you are always coinciding with the area, so it's not able to cut any flux. So this particular term will have contributions from this, and they will be plus. So v1 is opposite to the normal, so it will be minus v1 a1, and there is of course a rho. So this integral will be tantamount to this. This integral will be tantamount to minus rho 2 v2, rather minus rho v2 a2, and this will be equal to 0. So this plus this equal to 0. So this whole thing is 0. And that implies the expression for dH dt is equal to rho 1, rather just rho v1 a1 plus rho v2 a2 divided by rho a, and this is equal to v1 a1 plus v2 a2 divided by a, and this is equal to dH upon dt. So this is the final expression for how the height of the water changes with time. And we've made use of the very important concept that the surface, that one of the surface of the control volume has a velocity equal to the velocity of water. And it also brings into picture the very important concept that B can be locally varying. B over here is 0, over here is 0, over here is 0, over here is 0, but B for a certain surface can change. B need not be equal to 0 for the entire surface. Okay, B can vary over different parts of the control volume, and the choice often boils down to your experience and how best you can make a choice which reduces your own effort. Now, let us consider another problem in the same fashion. Let us consider a draining funnel. So we have a funnel like this and it drains water. So say the level of water at a given particular point of time is this. In fact, let me not draw the 3D-ish kind of figure. It will make things slightly complicated. Let me draw it as a side view. Okay, so this funnel is open. The area of exit is quite small compared to the entire the base diameter. Now it is given that the base diameter is equal to a radius r. At any point of time, the radius is small r and the height is small h, and this height is equal to capital H. Now, why does liquid flow from this point? So let us say that the exit velocity is VE. Liquid flows because of the pressure of the water, okay? Because of the pressure of the water, and it is given that the exit velocity varies with the height, and it is given as square root of 2gh. The exit velocity is equal to square root of 2gh. So the question is, what is the rate of change of the height when the height is equal to h upon 2? So now let me remove these little things. Okay, so the definitions are quite clear that this is small r and this height is small h. This angle is theta. So let us choose a control volume as shown by the pink line. In fact, the top line, let me make it orange like this. So for this particular control volume, over all the pink lines, B will be equal to 0. But we choose the control volume so that it moves with the surface. So that it moves with the surface. Meaning that the velocity of the water at the surface will be equal to dh dt, and this is going to be the velocity of this control volume also. So let us write down the conservation of mass. So ddt of integral rho dv plus integral rho u minus b dot n dA is equal to 0. So now this first term is ddt of integral, so rho dv will be this mass, so that will be equal to rho times the volume. So volume is 1/3 pi r square h plus, so rho u minus b dot n cap, so it will be rho u dot n dA for all surfaces apart from this top surface, and for the top surface it will be 0 because u minus b for the top surface is equal to 0. So now there is a relationship between r and h. Basically r over h is equal to tan of the half angle. So let me substitute this relationship over here. So we obtain ddt of rho upon 3 pi h cubed tan theta square plus, so what about this term? So at this particular term will have, so let's say this area at the exit is AE. So area vector is like this and the velocity is also aligned with the normal vector. So it becomes rho VE AE. and there will be a positive sign because it's exiting the domain. This is equal to 0. So that implies rho pi h square tan square theta dh upon dt plus rho e ve ae equal to 0. And rho e and rho are the same thing. And this implies pi h square tan square theta dh dt is equal to minus ve ae, where ve is now a function of h. So this becomes minus ae times square root 2g square root h. Let us take this h over here. Let us take pi and tan square theta on one side. So it becomes h raised to, so 2 minus half 3 by 2 dh dt is equal to minus ae square root of 2g upon pi tan square theta. And this implies dh dt is equal to minus ae. So dh dt at h equal to capital H upon 2 square root 2g upon pi tan square theta times capital H raised to 3 by 2. Okay. So this is the final expression for the rate of change of the liquid level when the height is equal to h upon 2. So now in this particular approach, we have considered that the control volume moves with the surface. Alternately, we can choose another control volume which is fixed. Let us see how to do that. So let me redraw the cone or the funnel, and let us choose this entire thing to be the control volume. So now for all the surfaces of the control volume, B is equal to 0. At any point, this is the height of the liquid. So let us write down the Reynolds transport equation in this case. So it is ddt of integral rho dv plus integral rho u minus b dot n equal to 0. So now when the red surface is the control volume, the velocity everywhere is equal to 0 for the control volume, and so this b will vanish. So it is simply ddt of integral rho dv. So now rho dv for this red volume will be rho dv for this water phase plus rho dv for the air. So it is rho water times half, not half, it will be 1/3 pi r square h plus rho air times the remaining volume. Now rho air is 1000 times, almost 1000 times lower than the velocity of the water. So this term is negligible with respect to this term, right? So we can sort of drop it for now. Similarly, for the flux also, so it is rho u, so what is it? Rho u minus b dot n cap dA. So this b will vanish. Let me just make this b vanish. So it is simply rho u dot n dA equal to 0. So what does this term give? This term gives, so at the exit it is VEAE. So this will be, so plus rho VEAE. But now there is one more term because liquid is being drained. So if you consider this to be the control volume, there is some liquid which is exiting the domain, but some amount of air will be entrained from this. Okay, there will be some entrained in air which will be entrained into this control volume. So there will be some rho air times V entrainment times area of base. But again, rho A is going to be quite negligible compared to rho, and V entrainment will also be quite small. So these terms can be neglected. So essentially you end up with ddt of rho water upon 3 pi r square h plus rho water VEAE equal to 0, and all the mathematics from the previous problem follows. So this is a combined control volume with air and water, and the fact that air has quite a low density compared to water causes all those contributions to the conservation of mass to vanish. But ideally you can do a conservation of mass for air control volume and for the water control volume separately. So air control volume will be moving with this velocity downwards, and the water control volume will be moving downwards. So you can essentially repeat the above problem for air. So in fact, if I pose this problem, if I have a funnel with one liquid over here and another liquid over here and another liquid over here, say 3, and the whole this whole volume on top of it is filled with liquid 3. So then you should be able to find out what the rate of entrainment of liquid 3 would be into the domain, into the cone. Okay. So it's just a matter of applying separately conservation of masses for all the elements. Of course, until and unless control this volume 2 remains bounded by the domain, conservation of mass for this domain will be absolutely trivial. Okay. So anyway, let's proceed. Let us consider a problem in which the density changes. So the problem statement is as follows. There is a vessel is connected to a pipeline by means of a valve, and the pipeline is carrying some gas at a higher pressure. And initially, so suppose the conditions of the pipeline are given as rho 1 and the velocity, say the velocity when this valve is open, the velocity at which it enters is v1, the area of this inlet is a1, alright, and say initially the pressure inside is P and the temperature inside is T, and the volume of the tank is say capital V. The cross is to distinguish it from velocity. So the question is what is the rate of change of density of the tank? So let us write down the conservation of mass for this control volume, the blue control volume. So the blue control volume has a zero velocity, it is a fixed control volume. So now ddt of integral rho dv plus integral rho u dot n dA equal to 0. So I have dropped b because the control volume has zero velocity, it's stationary. So now what is this? So it's ddt of rho times volume plus, so now if this is the control surface at this point, the gas coming in is having a flux through this, but the area vector is in this direction. So it will be plus rho 1 because the incoming density is rho 1. This will be minus v1, this will be a1. This is equal to 0. So now we get ddt of rho is equal to rho 1 v1 a1 upon the volume of the tank. So as you are pushing in more gas into the tank, you are causing an increase in the density. But of course, there are many thermodynamic assumptions behind writing this, and this is a very simplistic way of looking at it. Of course, it would depend on many other factors, the internal energy and the enthalpy and all these things. But this gives a first principle way of doing it. But remember that such problems are actually much deeper at a thermodynamic level. Lastly, let us look at another problem. It's called as the hockey puck problem. There's a game called as air hockey, so in which there's a table with a lot of dimples, and as a child I came across such kinds of things in one of those pantaloon big bazaar things, and it's a game where there is a disc and air is coming out from these holes, and because of the air the disc sort of hovers on the board, so it's like a frictionless disc. So then one person can hit it from this side and there's a hole and the puck can go in, and it's like playing football but on a frictionless table. So if I look at the table and puck arrangement from the side, it's like uh, something like this. The puck is floating in air. I mean, I'm exaggerating the diagram, but air is sort of coming in through the table, and you can approximate it as coming at from uniformly from the bottom. I mean, of course, it's coming out from discrete holes. We can assume that it is coming out like this. The puck has a radius of capital R, and suppose that this puck is floating in air at a height of h. Okay, the puck is floating at a height h. So let us draw this as the axis of symmetry. So the question is, what is the velocity field? So what is the velocity field? So now if I draw such a control volume, what is going on? Air is entering into this and then eventually leaving this point. Okay. So now we will neglect the effect of viscosity. By neglecting the effect of viscosity, it means that the velocity is uniform at all the cross sections. Okay. So neglect viscosity means uniform velocity. And this will be clearer in the later classes, but anyway, it's given that it has a uniform velocity. So then the question is, what is the velocity? So now if I redraw this slightly larger, this is the control volume, then fluid enters over here, say the inlet velocity is v, and suppose this is the center line, so this is suppose small r. So what is the flux of the inlet velocity v in? So n vector of this area is like this, so integral v dot n dA rho, this will be minus rho v in by small r square, right? Now the control volume is fixed, it's not moving, so air comes out from this spot. So let us write the velocity over here as v radial. Okay. So what is integral rho v radial dot n dA? This will be equal to rho. So now the normal vector to this area is in this direction, so it will be rho v radial times, now the area will be 2 pi r times the height. So now if we consider that air steadily, this for this entire volume it's steady, meaning air comes in, goes out, nothing is accumulated. So the Reynolds transport theorem will say this, where now this will be 0 because it's a steady flow, and this will have contributions from this surface and this surface. So essentially from the top view it will be a circle. So the area through which VR exits is 2 pi r times the height, the perimeter times the height. So it is integral rho u dot n dA for the incoming surface plus integral rho u dot n dA for the outgoing surface. This is equal to 0, meaning minus rho v in pi r square plus rho vr into 2 pi r h is equal to 0. And finally, so rho cancels out, pi cancels out, one of the r's cancels out. So V radial effectively comes out to be minus V inlet R upon 2H. So at R equal to 0, VR is equal to 0. And at R equal to capital R, it is equal to V in capital R upon 2H. Right? So it's a very easy problem which demonstrates the utility of a simple mass balance. In fact, we can make another problem, and I'll just give you the hints on how to do it. In fact, for anyone who has understood the last problem, this is going to be an easy one. So there's a solid disk and there's a disk which is coming down with a velocity of v naught. The radius of the disk is equal to r. So the question is, at any point h, where the height is h, what is the velocity? Rather, what is the actual velocity of the air? Not the actual velocity, the radial velocity. Let us call it as Vr again. So again, when this puck is coming down, it is pushing in air. So in this particular case, we will choose a control volume like this, which of this and this does not change, but this particular surface moves with velocity of the puck, that is v0 in the minus j direction, if I call this the j direction. Okay, so for this surface, u and b are the same, meaning u minus b will be 0. So I'm just gonna write it down very quickly, but I request you to do it step by step. So for this entire control volume, there is no, so the volume will be ddt of integral. So what is the volume going to be? It's going to be pi r square into h, right? This is going to be the, the volume, and this is going to be this plus. So now what are the fluxes? So the only flux that is going out is this one. So it will be rho Vr into h. Okay. So now this becomes rho. So rho cancels out, no problem, because the density is fixed. So okay, sorry. So this is rho Vr into h into 2 pi r. Okay? Because Vr is exiting the area which looks like this from the top. So the area through which Vr exits is 2 pi r multiplied by the height. So this is this pi cancels out. One of the r's cancels out. So rho r dh dt plus rho, already cancelled out the rho's. So plus Vr into 2h is equal to 0. So dh dt 1 upon h is equal to minus twice Vr upon r. So then you can integrate it over time and you can find out the expression. And essentially, again, you can try to rationalize the result. Okay, it's very easy to rationalize the result. And these ideas, I mean, this will be immensely useful in developing ideas of lubrication and all these things in the coming chapters. And it is very important to understand clearly and deeply what is going on, how at least mass is conserved. Once you understand how mass is conserved, you can sort of move on to the next step, how momentum is conserved. And that will be what the next lecture is going to be about. So with this, I close this particular session and